Okay, so before we continue the section 3.4, there's few things I want to address. So first of all, don't forget that the homework 7 will be due this Thursday. And so the material is actually getting more and more conceptual. So you definitely don't want to fall behind. I understand that last week was actually around the midterm week that people have a lot of midterms, exams, or maybe projects, but you actually need to really catch up. So I'm going to do some problems from the like similar problem as the homework exercise. So you're going to see, I hope that this is going to help you for finish up the homework 7. And another thing I want to address is that the homework 6 you turned in last week has been returned. And you might notice that like you got taken points off by the grader. So there's one thing that I noticed is that, for example, for one or two of the problem from 3.2, I think one of them is 12E and the other is maybe 20B, I believe. So some of the questions that was asking, say one of them, for example, say, does this following two vectors span the whole R3, right? So some of you actually give out the answer that, you can't without directly solving it, but just say you can't because you need three vectors. Mathematically, this is correct, but actually we haven't really covered this part. Then essentially you are using the future knowledge without carefully addressing it. So the thing is that then we actually haven't really talked about it until 3.4, where you need to first know the concept of dimension, and also you need to address that why two vectors is not enough, something like that. So we actually haven't really learned it until this section that we're learning now. So in 3.2, you should be careful. So this is also the same thing for the future homework, that there's a reason that they ask specific question in particular section, because they want to make sure, or we want to make sure that the students know how to use the techniques in that section for doing certain problem. So if you want to use so basically I told the grader that for anyone who actually use the future, like for example, say the knowledge from future section without addressing it or without using the correct method, then I told the grader to take 1 point off. So that problem, I think, worth 3 or 4 points. I only tell the grader, say, just take 1 point off. And actually, if you notice, if you ever go back to read the feedback from the grader, you should definitely do so. Our grader are very like responsible and then did a very good job by grading very detailedly and give a lot of feedback. So we are very lucky to have this very nice grader this semester. So please take advantage of having a nice grader that he provide a very nice detailed feedback. So you should definitely read it. So that's one issue I saw from the homework problem, that please do not use the future section techniques to do the problem in the previous section. There's a reason that we teach things in the certain order. For example, that if you're, imagine if you were taking differential equation class, right? And then the problem asks you to directly solve certain differential equation, and you just boom, give out some fancy formula, correct formula, even though, right? Mathematically, it's correct. But does it really means that you know how to do that problem? Not necessary, right? Even though you come out with a fancy formula that someone maybe calculated later on or find out from some software, but it doesn't necessarily mean that you really completely understand the knowledge that that section need to tell you. So that's why in this case, especially homework, I'm trying to be a bit strict that please, for example, if it's section 3.2, use the techniques that we learned in 3.2 to solve the homework problem in 3.2. And another issue is actually a little bit surprising to me is that, for example, I think it's number 20, A and B. I noticed that some of the problem actually do the wrong 20. And I believe the reason is that you directly use the number 20 from the nice addition. I've been talking about this since beginning of the semester, that my homework problem will be assigned from 10th edition. And I would not tell you that whether the problem are exactly the same as nice addition or not. This is your responsibility to get the correct textbook. So despite the fact that I actually say it's 20 A and B, but incorrect number 20 in nice addition doesn't even have part A and B. So I'm not sure that how people actually just directly do number 20, the wrong one, without even realizing there's no problem A and B. I'm actually very surprised to see that. Okay, so if you insist using the old addition, that's your call, but you need to take the responsibility to go ask your friends or classmates to update the homework exercise. As I said, the homework exercise, the problem in nice addition will be, some of them will be different than the 10th addition, like this time. Okay, so if you still are using the old addition, then you need to be careful, because in the future, you might do the wrong problem without even knowing it, and you will be taken points off. Okay, so please make sure that you get the homework number correct. So my homework, the problem I assigned is from 10th edition. Okay, so that's the several things that I want to address here. So any questions before we get started? Okay, so before I continue 3.4, I want to actually, because the last time we talked about 3.4 was actually last week. So I want to recall some of the definition, important definition from 3.4. And as I mentioned last Thursday, that when you studied chapter 3, especially I would say sections 3.2, 3.3, and 3.4, you should actually regard it as, or study it all together, because they're actually close related to each other. So think of 3.4 is kind of the combination of 3.2 and 3.3. So you, in order to understand what 3.4 is talking about, you actually need to know what's going on with 3.2 and 3.3. And those three sections are kind of all together, they're very close related. So in 3.4, we essentially combined the concept we learned from 3.2 and 3.3. So 3.2, the main thing is to talk about spanning set, right? Spanning set is regarding the collection of all. So you say, okay, I want to consider the span of some vector. Then you're talking about the collection of all the linear combination of those vectors. And in 3.3, we talk about, okay, if you give me set of some vectors, are they linear independent with each other, right? So this is 3.3. Then 3.4, we talk about, okay, if we have both criterion like that, meaning if you have n vectors, v1 to vn, and also a vector space, right? If this n vector is going to be the spanning set for this vector space, plus if this n vector are linearly independent with each other, then this is actually what we call the minimal spanning set. So basically these n vectors are going to be what we call the basis for this vector space. So technically, to be able to call, like say n vectors, the set of n vector to be a basis for the vector space V, first you need to make sure that these n vectors actually span the whole vector space V. Second, this n vectors has to be linearly independent, right? So first of all, you need to have enough amount of vector to span the whole vector space. But second, you also don't want to have redundant vectors. So you want to make sure they are linearly independent. So that's why we call it minimum spanning set. And then the thing is that if you already know that, say, we need n vectors, whatever the number is, right? Let's say if you know if you need n vectors to form a basis for a particular vector space, then this number, this amount of vectors is unique. Meaning that if you can find, so basically first, a set of bases is not unique, right? So for example, in R3, we can have the standard basis, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Those are one type of choices, the easiest one. But you can also find me 3 linear independent vectors, and that will also form the basis for R3. So bases, the choices of bases are not unique. However, the amount of vectors you need is unique, right? So basically, since this number is unique for the same vector space, then this number becomes some kind of signature of the vector space, okay? So basically, this is what we also learned last time, that if we know this number, right? In other words, if we know how many vectors do we need to form basis for this vector space, then this number n is what we call the dimension of the vector space. And we use this notation dim v to equals n. So for example, in R3, we already know, right, that the standard basis is 1, 0, 0, 0, 1, 0, 0, 1. You need 3 of them, right, to form a basis for R3. So you know the dimension of R3 is 3. So if you need to find me another basis for R3, then you already know in your mind that you need to look for 3 vectors, right? Exactly 3 vectors. Okay. So now, then we actually have some nice property here to help us to find the basis. So first thing, as I said, the dimension is some kind of signature. So by knowing the dimension before you do any computation or calculation, it's actually very beneficial. It's actually a big advantage. So first of all, if you already know the dimension is some number, let's say whatever this n is, if you know the dimension is positive, whatever the number is, then actually this theorem tells you that then it turns out that we don't really need to check the 2 criterion for forming a basis, right? So I just said, technically, the definition of having a basis is first, you need to make sure those set of vectors, those n vectors, form a spanning set, right? You need to make sure it spans the whole vector space. Then you also check the linear independency. But it turns out that if before that, if you already know how many vectors you need, or in other words, if you already know what's the dimension of the vector space, then you actually have a huge advantage here. Then it turns out that in this case, if you knew the dimension to start with, then you only need to check one of the definition here. So basically, that's essentially what theorem 3.4.3 says. Then the first statement says, if you already knew the dimension is n to start with, right? So if already know the dimension, then the first statement says that if you can find any n linearly independent vectors, then those n linearly independent vectors will automatically span the vector space. So for example, if you knew that a vector space has dimension 5, for example, then if you can find me 5 linear independent vectors, then those 5 vectors would definitely form a spanning set for the vector space, meaning then these 5 linear independent vectors will be a basis. So in other words, in the case 1, right, in the first statement, it tells me that if you can find me n linear independent vectors, then you don't need to check the spanning set criterion. Then automatically it becomes a basis. And vice versa, the other way around is also true. If you can find me n vectors that span the vector space, then they're automatically linear independent, right? So either way, it actually working out. So meaning you can see that either you only need to check n vectors to be linear independent, or you check whether these n vectors actually span the vector space or not. You don't need to check both. But be careful, this assumption, this statement is building upon the fact that you already knew the dimension, right? If you don't know the dimension, then you don't really know exactly how many vectors you need, right, beforehand, right? So if you just give me some random vector space where I didn't even know what the dimension is, then I wouldn't know how many vectors I need. Then I really need to check both definition. I need to make sure it's spanning set and also at the same time independency. But this theorem tells us if you knew the dimension for this vector space, which we do for a lot of examples, nice examples, then you only need to check one of the definition. So basically the remark is if you know the dimension of a vector space, then you only need to check one of the definition of basis, right? In some sense, this is what the this theorem means. Okay, so this is actually nice, meaning, for example, say, I always use this easy example, say in R3, right? We already knew the dimension is 3, okay? Then if I give you some vectors and ask you, okay, are they bases, right? Or in other words, if I ask you that, can you find me a basis, another basis for R3? Then all you really need to do is to find 3 linearly independent vectors, right? Because if you can find 3 linear independence, then it's going by the first statement, then it's going to automatically span the R3, right? Then because it's linear independent plus it's also a spanning set, then it's going to be a basis, okay? So this is basically quite powerful, or essentially the benefit of knowing the dimension. And another benefit, this is actually, I think, where people use the future knowledge for the section 3.2. The first statement is the one that I think that some of you actually use this. So this theorem tells you, again, if you know the dimension to start with, right? You can see that I need to put this disclaimer, right? If you knew the dimension to begin with, then, so let's say if the dimension is n, then the first statement of this theorem tells you that then if you give me fewer than n vectors, right? Let's say if the dimension is 5, if you give me 4 vectors, then it definitely cannot span the vector space. No set of fewer than n vectors can span. So this is actually, I think, what people was using. Some of you actually used in 3.2, but you can see that we actually haven't even discussed it until right now, right? So basically, this tells you also another huge advantage of knowing the dimension, meaning if you knew the dimension, right? Say if the dimension is 5, then if you give me any set of vectors less than 5, right? Then they cannot definitely span the whole vector space. Yeah. So no, as I said, like 3.3, it's focused on being linear independent. So this might sound too strict, but there's a reason that we put some certain homework problem in 3.3, because we want to make sure that people know how to solve a certain type of problem using certain techniques. So as I just said, please just focus on the certain techniques in 3.3 when you work on the homework 3.3. Because the thing is that there are a lot of things we haven't really justified. And also, this is mathematical logic. There are certain theorem or knowledge is based on the result from 3.3, right? If you use like the something from 3.4, then you need to make sure you already justified in 3.3, right? So there's also a logic issue. So please, as I said, if you're working on the homework problem in 3.3, just use the techniques from 3.3. If you're working on homework from 3.2, use the techniques from 3.2. There's a reason that I want to make sure that students know how to use a certain techniques. Then we can use a little bit more fancy, like techniques or knowledge, okay? Because actually, even though I tell you the fact now, to actually really prove this theorem, it actually needs some work. It's not that trivial, right? So I want to make sure that you know how to solve a certain problem directly without quoting some fancy remark, okay? So, other than this first statement, it's also, I think this statement 1, 2, and 3, some of them are I think 2 and 3 is kind of intuitive. So second statement says that any subset of fewer than n linear independence vectors can be extended to form a basis for the vector space. So what does that mean? So we already know in order to qualify as a basis for this vector space, we need exactly n vectors, right? So now if I start with a set of, so let's say if this number n is 5, for example, let's pick a concrete number. If the dimension is 5, if you give me a set of, say, 3 linear independent vectors, I already know these 3 vectors cannot be a basis. But if you start with 3 linear independent vectors, then you can keep adding vectors, right, to form a basis, because I need 5. But in order to add it, you actually need to be careful. You want those vectors you add to be also independent, right? So first, you already have 3 independent ones, right? And it's not enough. I know it needs to go to 5, for example. Then you need to add a 4th one, right? It's more like a try and error. It's not, there's no systematic way because basis is not unique. So once you add a fourth vector, you want to pick this fourth vector such that these four vectors altogether are linearly independent. Once you make sure that, then you say, okay, 4 linear independent vectors, still not enough. I need another one to form 5 linear independent vectors. So you need to add the fifth one, then such that you need to check all these 5 vectors are linear independent. Then these 5 vectors will be the basis. So once you have like some smaller amount of number, then you need to first make sure that the new things you add is linear independent. Okay, so that's basically what the second statement said. Even though you don't have enough linear independent vectors, but you can actually extend it to form a basis. Okay, so that's essentially the, and I want to say that how do you extend it? Basically by adding new vectors that are linear independent. So I'm going to do a problem like this later on in a minute. And the third statement says that any spanning set containing more than n vectors can be pared down or cut down to a basis, right? So now this is the other scenario, right? So that's, again, I'm pretending if the dimension is 5. If you give me 6 vectors, then I already know some of, or maybe 7, let's say, right? Then you already know if you give me 7 vectors, that's going to span the vector space V. Then, okay, you have the criterion for spanning set, but you already know you need exactly 5. 7 is too much, right? So if you tell me, say, okay, I know the dimension to be 5, but you give me 7 vectors that's going to span the whole V, then something are extra. So you actually can see that, okay, then you need to cut down some of them to really give you the correct number of bases, right? But if you ask me that which one I should cut down, there's no systematic way to do it. You really need to make sure the one you cut down are really redundant, meaning the remaining 6 are independent, right? Or actually, I should say the remaining 6 can still form the spanning set. Then you cut another one, right? Until you reach 5 vectors, which are still the spanning set and also linear independent. Okay, so there's some, so you will see that there's some try and error. Even though I said that, okay, knowing definition gives you some advantage, but at the same time, you also want to make sure that you really understand the concept here, because sometimes I can just twist the problem a little bit. Then if you just kind of blindly remember some fancy, like for example, fancy remark or theorem without knowing really how to use it correctly, then there will be a problem. And also at the same time, I want to make a remark here that be careful that being linear independent in general are a different concept than being spanning set. One of them is that you want to create enough of linear combination vectors such that you hit every vectors in the space. The other is that it's the other around. You want to make sure that they're linear independent, meaning there's no redundancy. They're actually not the same concept, okay? So which means that you can have 3 linear independent vectors, but they may not actually form the spanning set for some other vector space. So you want to be careful. These two concepts generally are different, but in certain situations, one of them may imply the other. But you want to make sure that you really know that which case is that. Okay, so you want to be careful. That's why I say it's more conceptual than you think. Okay. So this is so this 2 theorem here. I'm not going to prove it because it actually are too theoretical, but it will give us some nice framework to do certain problem. So first, this is just some remark or some like thinking. So I just simply question, right? Then now, because we know this theorem to start with, then if I ask, can these 2 vectors be a basis for R3? Then now we can really say that, okay, no, we know it can be, right? Because one of the like this first statement here tells us that I already know the dimension for R3 is 3. And no set of fewer than 3 vectors can span the whole thing, right? So basically 2 of them cannot span the whole R3. So basically you can answer that, okay, we know the dimension of R3 is 3, right? So 2 vectors. So actually if I want to be really precise, I would say by theorem 3.4.3, 2 vectors cannot span the whole R3, right? So you need to mention that that's because you know the dimension here. And of course, I can ask the other way around. I can ask you, can 4 vectors form a basis for R3? The answer is also no, right? Because you know you need exactly 3, right? 4 would be too much, essentially, right? And so you need to so basically knowing those theorem will give you a little bit advantage, but it doesn't tell you that you don't need to justify this. Also, you need to give me some reasoning here. So another
statement you were saying,
yeah.
With 4 vectors that it doesn't span. I'm not sure I'm quite tracking that.
Oh no! So if 4 vectors, then you need to be careful, right? Because 4 vectors depends on which 4 you give me, right? It may not span, it may, right? But 4 vectors, you know, it cannot be a basis because it will be either. So depends,
That's
right?
what I missed. It can't be the basis. Okay.
It can't. It cannot, because we already know that the number of vectors you need to form a basis is fixed, right? So we already know in R3, the dimension is 3, meaning we need exactly 3 vectors to form a basis. So if you give me 4, then it's definitely like not okay. But it also depends on which 4 vectors you pick, right? If you're unlucky, then if you are really, really unlucky, you give me random 4 vectors, then it's still possible that those 4 vectors would not span R3, right? For example, if I give you this really bad cases, right? This is very kind of silly example. Okay, so I give you 1, 0, 0, 2, 0, 0, pi 0, 0, 0, 0, 1. Okay, 4 vectors in R3, right? But you can see that
the
first 3 are linear dependent, right? So technically, you know that these 2 are essentially redundant because this in the span of 1, 0, 0. So technically, you only have 2 independent vectors, right? So that's why it really depends on which 4 you give me. If it's 2, then you can just automatically say 2 is definitely not enough. But for 4, right, it may be too much. It may still be too few, depends on the vector. But what I can say is that if I knew, right, that's why I say it's not that like a clear cut. It really depends. So if you told me you have 4 vectors, whatever those 4. But first, you already told me if I knew this 4 can span the whole R3, then that means at least we hit one of the criteria for being a basis, right? We know this 4 will actually form a spanning set for R3, right? Then it's not going to be the case I just showed you. Then it's not as bad, right? So if you have 4 vectors that's going to span the whole R3, then again, but it still be too much because we know we need exactly 3. Then in this case, in the second case here, if you already knew they're going to span the whole R3, but there are 4 of them, but we know the dimension is 3, then right now I can tell you they are not linear independent. One of them will be redundant. So did you see that those 2
basically what we're saying here is that you've got 4 vectors, you can span R3, but they may not form a basis. Is that accurate?
Yeah, you can span the R3. So what is the definition for span? Span just means that if you take the linear combination of those 4, it will reach every vector. Or in other words, every vector in R3 can be written as a linear combination of those 4, right? This is essentially the definition of span. So you could have 4 vectors that span a space, but it doesn't necessarily tell you whether they're independent or not. And in this case, because I know exactly the dimension of R3 is 3, so I already know these 4 vectors would have to have some redundancy here. And you can actually check that those 4 would not be linear independent. That's why if they're not
you.
independent, yeah, then they cannot form a basis. Yeah, so that's why there's a lot of subtlety here. So you really, that's why sometimes I'm very hesitant to just refer to some fancy statement, because there are certain situations you need to kind of depends, like need to see that what's going on with a specific example here. Okay, so now I want to also do some example regarding the remark a little bit above here, that if you have if you know the dimension, and if you have a set of vectors which are linear independent, but like fewer than that particular number, how do you extend it to form a basis, right? And also, if you have too many vectors, even though if you have too many vectors, how do you cut down, right, the vectors to get the correct number? So I want to at least do these two examples so we can actually see more concept here. So first of all, I'm going to use R3. That's the kind of the easiest example I can work here. So for R3, I said, okay, I already know V1 and V2 to start with. I say, can you find me a third vector such that this 3 will form a basis? Then first of all, we know 3 is the correct number, right? Because R3 has dimension 3, okay? So now the thing is that we say, okay, in order to, since we already know the dimension is 3, so the only thing we need to make sure is that we have 3 linearly independent vectors. Then by one of the theorem that we just saw, if we have 3 linearly independent for a 3-dimensional vector space, then those 3 vectors will automatically span the whole vector space. Then we definitely will have a basis, right? So this is essentially one of the theorems says that if you have the correct number of the vectors, if they're linear independent, they implies the spanning set, right? So then we only need to check one of the criteria. But if you want to first, before you even find the third correct one, you need to make sure at least the first 2 that I give you here to start with are linear independent, right? If those 2 are not linear independent, then we are done. Then we really need to find another 2, right? So first we observe that this V2 vectors, right, is not a scalar multiple of V1, right? So you cannot multiply V1 by some scalar number to get V2. So we know that this essentially what tells me that these 2 are linear independent, right? This is something we talked about in previous section. Then, okay, first we make sure the first 2 that we start with are independent. Then we find the third one, and hopefully these 3 vectors together are linear independent, right? But then if you ask me that, okay, how am I going to come up with this third one? Unfortunately, there's really no systematic way, right? Because you technically you have so many vectors out there you can choose, right? So this is more like a try and error like scheme. To be honest, there's no really the better way. And I would say the best strategy here is probably trying to see that like you trying to pick a vector and check the linear independency, right? So, but first there's I'm going to do some silly try and error. This is more like for understanding the purpose of understanding, right? So this is try and error scheme. Okay, so first let me ask you the question. If I know V1, V2 are these 2 given vectors, right? I want to pick the third one to form a basis. So the first question I'm going to ask is, can the third vector V3 be 1, 1, 1? Can anyone tell me?
No.
V1 plus V2 would equal that.
Right. So so Emmanuel also say no. Why? What's your reason?
Because you can cancel it out by just doing the addition.
Yeah. So basically, you can see that 1, 1, 1 actually is like this is kind of observation, right? This is also essentially my try and error scheme is to tell you what things not to do, right? So if you pick 1, 1, 1, of course, this cannot be your the third candidate, because then this one would not be linearly independent with V1 and V2, right? So the answer is no, since essentially V3 in this case would be just V1 plus V2, right? So this tells you then in this case, if you can write one of the vector in terms of linear combination of the other 2, that's definitely what we saw in the beginning of 3.3. That essentially means that they're not independent. So this tells you that V1, V2, V3 won't be linear independent. So that tells you that, yeah, you definitely want to avoid this choice, right? So you want to be careful. If it's so obvious that you pick something that can be a linear combination of V1 and V2, then that's the thing you want to avoid, right? So I want to show you this kind of silly example to tell you that, okay, there's something you don't want to do. But then, to be honest, I also don't have the best way to tell you how to pick the correct one. Again, as I said, this is more like a try and error. So what I noticed, for example, what I observed is that, okay, V1 is 1, 0, 0. V2 is 0, 1, 1, right? So they kind of look very similar to standard basis, but not yet. So what I would pick is the third vector would be something only have the second coordinate or the third coordinate to be non-zero. So I can try this. This is really try and error, right? So I'm going to just pick one and check, right? So then again, just pick one and check, right? So say, okay, I say maybe V3 is 0, 0, 1. Okay, so then if I pick one, right, 0, 0, 1, you can see that it's not obviously to be a linear combination of V1 and V2, right? So you say, okay, that might give me hope, right? But the thing is that like you cannot really like directly say it without checking it. So I say, okay, I'm checking linear independency, right? So I want to check whether V1, V2, V3 are linear independent or not, right? So then go back to 3.3. That's why I said somehow in order to know 3.4, you really need to get 3.2 and 3.3 done, right? So I'm going to solve C1 V1 plus C2 V2 plus C3 V3 equals 0, right? This is something we learned in 3.3, right? But as you can see, because these three vectors are all in R3, right? So they're going to form, essentially this is the same as solving the homogeneous equation, where essentially A is just the, so A is just, you put the V1, V2, V3 to be the column vectors. So V1 is what, 1, 0, 0. And this is 0, 1, 1, and V3 is 0, 0, 1. So I'm solving this system, right? So this is really just put V1, V2, and V3. I'm going to be a bit fast here because this is something that we have done in 3.3. So you're solving this 3x3 system. If you still remember, in 3.3, we mentioned if you're solving a square system, right, when you check the linear independency, right, then you can actually just directly check the determinant, which is just check the determinant of this matrix. Okay, as you can see, I mean, because I picked this very easy example, so you can really see that it's directly equals 1 because it's triangular matrix, lower triangular. So you can just multiply the diagonal. So you know the determinant is 1 right away. If it's determinant non-zero, this means that you have unique trivial solution for C1, C2, and C3, right? So basically this means that, yeah, indeed, V1, V2, V3 are independent. And that's essentially how you can really tell me once they're linear independent, 3 of them, right? And we know dimension of R3 is 3. So we know that since dimension of R3 is 3, so these 3 will form the basis. So you can see that these 3 vectors, even though they're almost the same as standard basis, but they're not. So you can see that other than standard basis, we actually pick another different choices. And of course, you can cook up with something more complicated, right? It's not necessarily this easy number. You can come up with 3 linear independent vectors And that will also give you another choices of bases. You actually can have infinite many choices of bases here. So that's why basis is not unique, but the amount of vectors we need is unique. And we know it's exactly 3 for R3. Okay, so any question for this example?
I just tried vector 0, 1, 0. That also would have formed a basis. Is that correct?
Yeah, because you can actually see, right, 0, 1, 0 would actually should give you like determinant to be non-zero, right? Yeah. So someone just asked me, can I use? So did I just use arbitrary vector and test it? Yeah, I did. But I know that my goal is to make sure that when I put it in the like a matrix, right? Because I know what am I going to solve eventually, right? If you pick a third vector, right, then eventually it boils down to make sure the determinant of these 3 vectors, essentially when you put it as a column, right, vectors, the determinant of this matrix, I want it to be non-zero. But since the first 2 vectors I give or I put it here are kind of easy, so I can easily see that which third vector I need such that the determinant has to be would be non-zero. That's essentially my strategy here. But unfortunately, if I give you something more complicated, V1 and V2, then there's really no systematic way. You really have to just test it. That's why I say it's more like a try and error scheme. There's no systematic way, right? Because as I said, you can have so many choices. Yeah. So you can pick one that's different than mine, right? So that's why in the homework for these 2 sections, you might come up with different different answers or different type of answer than your classmates, right? You might have, for example, for this type of problem, if you pick you might pick different third vector than mine. That's totally okay and totally common for this type of problem. And another problem I want to do is essentially, this is the case that you may have you have too many vectors, right? So I said, okay, I give you this 5 vectors, right? And I said, I want to use this 5 vector and see whether they form a basis, right? Among those vectors, right? So it turns out that you might actually, like, this is exactly like the issue I was addressing earlier. Even you give me 5, if you're unlucky, you may actually not having the correct enough vectors, in the sense that you would find out that some of them are actually already not independent with the others, right? So I'm just trying to, so I write down this problem very briefly. So I just say find basis for R3, right, among these vectors. So how are you going to pick, right? There's so many ways to do it. As I said, it's also more like a try and error. So first I can, in order to take out or delete the bad one, I can see that, okay, is there any vector among those 5 that I already see that is linear combination of the others, right? Then you can actually see that, okay, or in other words, in order to find basis for R3, I need to have 3 independent vectors. So I'm going to find 2 independent to start with, right? So you already know these 2 are independent, right? How would I know? Because they're not multiple of each other. And someone just tell me V3 is the bad one, right? So you start with, actually, I called it U1, U2. Let me just call it U1 and U2 so we can distinguish between this example. So we already know that if we start picking U1 and U2, then U1, U2 are linear independent because they're not multiple of each other. And the third vector, you already see that it's 1, 1, 0, right? Which is actually just U1 plus U2. So you already know U3 is the bad one, right? So we observe something very obvious that U3, if I call it U3, U4, U5, U3 is actually U1 plus U2, right? So you don't want this. Meaning, if you look at U1, U2, U3 altogether, those 3 are not linearly independent. So having U3 on top of U1, U2 is not going to help you. Then you ask, okay, is U4 okay? Probably even worse, because you can see that U4 is just double of U1, right? It's also not going to help you. Okay, so U4 is 2 times U1, right? You don't want it as well, right? And also U5 as well. U5 is like some multiple, even it's pi, right? Pi times U2. So you can see that, okay, I start with two vectors, which are obviously linear independent, right? You can also start by picking some other two independent vectors, right? But you're going to see that unfortunately, U3, U5, U4, and U5, those three, they're not going to give you a correct third linear independent vectors. So in this case, then it turns out that, okay, you only have two that you can use, right? In this case, two is not enough. This becomes kind of back to the situation that we start with, right? Like this example, you only have two independent vectors. Then in this case, you just need to add a third one, right? But you can see U1, U2 is already so simple in the sense that one of them is 1, 0, 0, the other is 0, 1, 0. I think like you will need to be very, very bad luck in order to pick the wrong U3, right? So I just pick some, you can actually pick, I called it V3, the correct one, to be 0, 0, 1, right? Then 1, 0, 0, 0, 1, 0, this is U1 and U2. And 0, 0, 1, this is what I call the correct V3, will form a basis for R3. Or if you want, or you can pick, right? As I said, there should be a lot of choices. So you can pick V3, just find something fancy, right? Then you can check the determinant, right? In this case would be 1, 0, 0, 0, 1, 0. That's the first two. And you want to add these three. It will be non-zero, right? So you can also pick V3 to be whatever, right? Yeah, so I mean, it's not, it's actually, you should think of this as actually a good situation, meaning you actually have a lot of choices. Unfortunately, math is always like that, right? Even though, yeah, we do have certain correct answer, but a lot of time, there's so many ways you can get to the same thing, right? You don't, like, for example, as an engineer, you want to have so many different tools that you can solve one problem rather than having only one tool and you need to search for that one particular tool. Then you need to think, what if you don't have that one particular tool, then you're doomed, right? So actually sometimes having more choices is good, because when you're trying to, for example, when you're trying to deal with certain situation, you may not have the luxury to stick with certain situation or certain number or tools. So you need to have more choices, right, to deal with the situation. So having more choices, like, it's not necessarily bad, actually. And that actually really tests you whether you understand the concept or not. Okay, so I want to, as I promised, I want to do some problem that's related to the homework that I assigned. And I think it will definitely help everyone on doing the homework, which is due Thursday. But before I do that, I want to just mention one example. And unfortunately, I want to rather spend more time on doing some examples similar to the homework problem. So I just want to say it out loud that this example exists, and then I will refer everyone to read the textbook for the explanation. So this example here is just say, okay, back then we have this vector space, we call it Pn, right? It means you collect all the polynomial of degree up to n minus 1. For example, P3 means you collect all the polynomial. This is a vector space of all the polynomial of degree up to 2. And we know Pn for each given n is a vector space. But if you change the space, you make it even larger. Then we have this space, vector space, which is essentially if you collect all the possible polynomial of all orders, then this is also a vector space. But it turns out that this vector space is going to have infinite dimension. And this is the example I mentioned earlier, that indeed there exists some vector space whose dimension is actually infinite dimension. So I can actually rigorously prove it. And actually, I remember the textbook actually prove it, but I don't have time to explain it here. but I can give you the intuition that why the dimension is infinite, right? Rather than finite dimension, rather than a fixed number. So you can think of, okay, if I claim the dimension to be a finite number, so I say, okay, I think 10 is enough, right? I only need 10 vectors to form the basis. Then you can see that because I'm collecting all the polynomial of all orders, right? So if you tell me that, oh, I only need 10 vectors to form a basis, then I will say, okay, then what about, I can definitely find something up to like a very large degree, right? Then 10 polynomial would not enough to form the correct spanning set. And if you say, okay, then let's pick a much larger number. I say, okay, I only need 10,000 vectors. So assuming if the dimension is 10,000, right? Then I will say it's not enough because you can range from the polynomial 1 or x squared all the way to 10,001, right? Then you're not going, or even 20,000, right? So so you definitely would not have enough. Then you can keep adding polynomials, right? So this basically tells you that there's no way you're going to stop at a finite number, right? Because you're collecting all the polynomials of all order. So you will never have enough, or I should say you would always having to add more vectors to form your basis. That's the rough reason why the dimension of this vector space is infinite many, right? So that's why I just want to show you that, yeah, there might be some vector space whose dimension is actually infinite many, right? Or you can say infinitely, meaning that you cannot just give me a finite number of vectors which is going to form the basis. Okay, so this is a little bit more theoretical, but fortunately that when I ask the question, because I cannot ask you to write down infinite many thing, right? So if I ask you a question, or even to find the basis explicitly, I will give you a vector space which has only finite dimension. Okay, so the following example of this one, I pick out from the exercise 7 in session 3.4. And I didn't assign this one, but I actually assigned the other one, which I forgot the number. I think it's maybe 11, which is very similar to the concept here. So I want to do a model example. So hopefully you can use what you learned here to do other problem. So this problem says find a basis for a subspace, and they call it S. So it's a subspace of R4. So because it's a subspace, so you don't know whether the dimension is 2 or 3 or 4, right? Because it's not R4 itself, it's some subspace, okay? But this subspace, I have a correct or explicit description. This subspace consists of all the vectors in this form. So all the vectors in this subspace will look like A plus B, A minus B plus 2C, B and C, where A, B, C can be actually any arbitrary number. So when you see things like this, especially when you have some freedom of some variable like A, B, and C, this should trigger you to think of that then this is something related to linear combination. Okay, so my first strategy is that, okay, if I want to know what this space really looks like, I want to see that how can I write this arbitrary vector V in the subspace as a linear combination of some vectors. So the idea is express any vectors V in this subspace as a linear combination of some vectors. So you want to see that whether you can do that. Okay, so the trick is the following. I already tell you that any vector there should be in this format. So you want to rewrite this format so it looks like linear combination of some vectors. So you look at, okay, arbitrary vector in S will looks like A plus B, A minus B plus 2C, B and C, okay? Then you can see that this A, B, and C should be our coefficients, right, to form the linear combination. So what we do is we separate this vector, right, in terms of like something only related to A, or something only involve B, and something only involve C. So I can always rewrite this vector like this, right? So you can see that I pick out the things that only depends on A or B or C. So you can see that I can always decompose this vector V in terms of 3 type of vector, right? And each one only involve one coefficient, right? So now you can see that then what I really saw here is, okay, if you factor out A, then the first one is 1, 1, 0, 0. And second one is, if you factor out B here, then you have 1, minus 1, 1, 0. And the last one is C times 0, 2, 0, 1. And A, B, C can be any number. So once you do this treatment, then you're essentially telling me any vector V in this subspace S looks like linear combination of these 3 vectors, 1, 1, 0, 0, 1, minus 1, 1, 0, and 0, 2, 0, 1, right? So basically what does this tells me, right? Then if you call this U1, U2, and U3, right? So since any vector V in S is a linear combination of U1, U2, and U3, then this basically tells you that these 3 vectors span the vector space S, right? So that's the first thing we need to realize this. We need to find the vectors. Before we can find the basis, we need to find which vectors are going to be the spanning set, right? Because remember, first of all, we don't know the dimension for the vectors, this subspace S to start with, right? It's a subspace of R4. So we don't know. It could be dimension 4, it could be dimension 3, it could be dimension 2, could be dimension 1, right? I don't know. So if I don't know the dimension to start with, then unfortunately, I need to check the 2 definitions of finding a basis. One is the spanning set, one is linear independency. So right now, what I'm working is, because they tell me explicitly what the arbitrary vector general format looks like. So I find out that, oh, okay, it's actually always look like a linear combination of these 3 vectors. So right away, I check my first criterion. I know these 3 vectors I just write down here form a spanning set for S. But now, let me ask this question. Is the dimension of this vector space S 3 or not? Or we don't know yet. So what would be it? So my question is the dimension of this space necessary 3? Just because the spanning set has 3 vectors. Can anyone tell me?
Well, but if it was more than 3 and we only have 3 vectors, then it means that it couldn't be the case, right?
Yeah, so it will be at most 3, right? But could it be less? At this point, could it be less?
Well, can't you only get linear independency with like the right amount of vectors?
What do you mean right amount? Because I don't know the dimension of vector space S, right? Because S is a subspace of R4. I don't know the dimension. Yeah.
With the same amount of vectors as the dimension of the subspace?
So how do you, so my question is, I don't know the dimension of this subspace S, right? So I'm asking, is the dimension 3, right? I don't know. So if you don't know yet, then how do you know what would be the right amount?
Well, we proved linear independency, so wouldn't that be the condition for it?
So, but we haven't proved linear independency yet, right? Did we?
Not exactly, but I kind of eyeballing the 3 vectors there. They look at linearly independent.
Yeah. So my question is, right now we only say that these 3 vectors span the vector space S, and we don't know the dimension of this vector space S yet. So before we can even say that the dimension of S is 3, we need to show that these 3 vectors are independent. If they're not independent, then it means you can use less or fewer vectors to form the spanning set, right? So at this point, right, because I haven't checked the linear independency yet, this is exactly why I put this problem, because a lot of people confuse the concept of spanning set and linear independency. They're two separate concepts. At this point, I didn't tell you anything about whether these three vectors are independent or not, right? Of course, you might be able to directly see it, but actually it's actually hard to directly see it, right? So you actually need to check it, right? So at this point, if I stop here, I didn't give you enough argument to say what will be the dimension for S. I don't even know whether these three vectors actually form a basis or not, because they could be dependent with each other, right? As I keep emphasizing, being a basis is stronger than being a spanning set. Being a basis, you need both spanning set and linear independency. Here, I only show you, yeah, these three vectors form a spanning set for S, but they may not necessarily linear independent. So we actually need to check whether they're independent or not. So the next thing is that we have the spanning set, right? So U1, U2, U3 span whole S, but we still need to know, because to form a basis, we need to make sure they're independent. So we need to check the independency. So the first step, we got the first step. Second step, check linear independency. Okay, so now you can see, okay, I have three vectors, right? Which actually is some three vectors in R4. I don't know whether they're linearly independent or not, right? Because it actually doesn't go beyond four vectors, right? So I really don't know until I check it. That's why I also insist that you should know how to directly check it rather than using some theorem, because if you don't know when you can use the theorem, you might use it completely wrong, right? And imagine if I give you a very big problem in the exam, I ask you to check everything, you just give me 2 lines and then you use it incorrectly, then you pretty much lose the whole points of the whole problems, right? So now check linear independency. So we want to show that C1, U1, or actually want to solve C1, U1 plus C2, U2 plus 3, U3 equals 0. This goes back to 3.3, right? So now let's solve it, right? And unfortunately, now you see that U1, U2, U3 have 4 coordinates, right? They're the vectors in R4, but you only have 3 of them. So if you write, if you want to solve it, it's going to become the system, some homogeneous system. And your matrix is going to look like, as I said, U1 will be in the first column, right? And U2 will be 1, -1, 1, 0. That's U2. And U3 is 0, 2, 0, 1. So you're solving this non-square system. So you cannot even use the determinant, right? Then you really have to solve it. Just essentially Gaussian elimination. Okay, but this is not too bad because we already have a lot of like 0 here. So, okay, so I'm going to use this 1 trying to cancel out this. Okay, so I'm not going to write exactly what I did, but you can, you know that my goal here just to make it as simple as possible, right? And then after this, I'm going to swap the row 2 and row 3. So I can have some pivot 1. And after I reach this point, you already kind of know that, well, this is very easy to solve now because like, I mean, you only have this 1 here, you can cancel out this -2. You also can take this 1 to delete that. So eventually I'm going to skip some step here. You should be able to see something like this, 0, 0, 0, 0, 0, 1. And I'm going to stop here because then, and then you can also actually cancel out this because using the 1 here. So eventually, if you really, really simplify to REF, okay, I should supposed to switch the bottom row with the third row, but you can actually see that now in this case, then you solve C3 to be 0, and C2 to also be 0, and C1 to be 0. So this tells you that you only have unique trivial solution, meaning then U1, U2, U3 are independent, linear independent. At this point, once you really show me that these three vectors are linear independent, then you can really tell me, okay, because they're linear independent, plus they form a spanning set for S. So these three vectors really form a basis for S. Okay, so now we can finally say that these three vectors form a basis for S. And this is a good example showing you that if you have a subspace in R4, right, it's a subspace, it's not the whole R4. So you might have a subspace which has less dimension than R4. But before we do a whole bunch of checking and computation, you really don't know what's the dimension of S to start with, right? Think about it. You can have the three-dimensional space, right, R3, but you can put a plane, right, a flat plane in R3. We know plane is a two-dimensional stuff, right? But it can sit in R3, right? That's a subspace, right? So before you really do further investigation, you don't know what's the dimension of this subspace. Then if they at least give you like what's the typical format of the vector, then you first trying to find out what will be the spanning set for this set, right? Then you check whether this vector you have for the spanning set are really independent with each other or not. Then once you check the spanning set and independency, then you can really say that they form a basis. So that's why this is much more conceptual than you think. So my follow-up question is the following, right? If a vector space, let me put different notation, different vector space, right? Maybe I should use different different notations in, this is different question. If I have a vector space W and I tell you it's the span of three vectors for some arbitrary vectors, V1 and V2 and V3 that I don't know, right? What would be the dimension of this vector space W, right? Can anyone tell me? If I just tell you, I don't know what vector space W is, and I only know it's the span of these three vectors for some.
Yeah, without knowing that V1, 2, and 3 are linear independent, then yeah, you
don't
don't
know.
the dimension.
Yeah, you don't know the dimension at all, right? It could be 3. It actually could be less. So the answer is not necessarily 3, because this is exactly what I was talking about, right? You might have 3 vectors that can form the spanning set of W, meaning any vector in W is linear combination of V1, V2, and V3. But yeah, like these 3 vectors may not be linear independent at all, right? So the thing is that what you can only say is that because you already know that these 3 vectors could span W, right? So you know 3 is enough for W, but you don't know whether they're independent or not. You don't know whether there's actually a redundancy or not, right? So the only thing we can say is the dimension of W is at most 3. But without knowing further information or explicitly what vector is, you don't know whether they're independent or not, right? So you want to be very careful, because this is actually a lot of, like this is the concept you're going to use for the homework, right? For the homework, especially in 3.4. And I think this will help, because this is actually the key part here. Okay, so I hope by doing this will clear up a lot of doubt. Well, I think some of the homework, I forgot the number, maybe 3 and 5, and also 11, I believe. Some of them you need this concept, okay? So this section, even though when you read the textbook, it looks like theoretically, but it actually has a lot of like information or concept here, and there's a lot of trap here. So that's why I want to warn everyone, even though I tell you a vector space is span of some vectors, it does not tell you that what will be the exact dimension unless you check the linear independency, right? So again, being a basis is you need to, so how do you know the dimension? The safest way is to find the correct set of bases. If you can find me, if you can prove me that you can find, say, 2 vectors or 3 vectors, that's going to be your basis. Then the amount of vectors that form the basis is the dimension, right? So the best strategy is to confirm the dimension of this vector space is to really explicitly find me a basis, right? Then then you know that you're safe, right? Because if you can find, say, 4 vectors, which is going to form a basis for some vector space, then you know the dimension is 4, right? Then you don't need to guess what's the dimension here, right? So one way to do this is to really find the correct basis. For example, like this problem, right? I don't know what's the basis, right? I don't even know what's the dimension for this subspace S to start with. But first, I know that, okay, I rewrite the vector. I know it looks like a linear combination of 3 vectors. So I first got the conclusion that this vector space S is the span of these 3 vectors. But at this point, exactly what I said, you don't know the linear independency, right? So you can only say at this point, the dimension will be at most 3. But I don't know, it could be 3, it could be 2, it could be 1, until I really check the linear independency. So I check they're all independent. In some sense, it means they're not redundant, right? They're necessary, right? You need every single one. So then in that case, it said, okay, since it formed a spanning set of S, plus they're linear independent, so they really form the basis. Once you can find the correct basis, then we really know that the dimension is 3, right? That's basically how we should approach this type of problem. Okay, so be careful here that there's a lot of concept. So actually I spent quite a lot more time on 3.4 as I expected. So I want to start the change of basis a little bit so I can give you some motivation for the 3.5 that we're going to do on Thursday. So I want to recall this thing that I didn't mention this theorem back in 3.3 because we really don't need to use it until now. So I want to just address it now, and you can think about it. So one good thing about having a basis, right? Or actually having I should say one thing of having a basis is the following, right? If you know that this n vectors is a basis for the vector space, this is actually equivalent to say that any vector v in the vector space can be written as a unique linear combination of these n vectors, meaning these coefficients ci's are unique. Okay, so you might wonder that, oh, why I need this n vector to be basis? If it's merely a spanning set, then they already can be written as a linear combination, right? The key point is this word's unique here, right? So keep in mind, having a basis is something stronger than just the spanning set, right? It's the spanning set plus linear independent. So if you use the property of being a spanning set, then of course, any vector v in this space can be written as a linear combination. But the question is, it may not necessarily be a unique one. So then essentially the property or the idea about being linear independent guarantee that once you write down the linear combination, it has to be unique. There's only one way to decompose your vector. And that's essentially why we need 2 criteria, spanning set and independent. Spanning set guaranteed that your vector v can always be written as a linear combination of this n vector. Having linear independency would guarantee that once you write down the decomposition, the combination like this coefficient are fixed. For example, if you tell me v is, say, equal to 2u1 minus 3u2 plus 4u3, let's say if I stop at 4, right? If that's just 4 of the a vector. Then if I say, okay, if I know u1, u2, u3, u4 form a basis for my vector space, and if I know one of the vector v, right, whatever that vector is, is a linear combination of U1 to U4 in this coefficient, then there's no other way to decompose this vector V, right? If there's no other, so basically it tells me that 2, -3, 4, and 1 is my only choice to rewrite V as a linear combination if those 4 vectors are bases. So this tells you something very strong. Once you give me a set of bases, right? Once you give me a choice of bases, then any vector can only be written as one unique way of linear combination, right? Then you can see that then this coefficient here somehow become the signature or ID of your vector V, right? So that's the beauty of it. Once you know you have a basis, then you can write any vector in terms of one particular unique way as a linear combination. Then all this C here, C1 to Cn, is what we call the coordinate of V with respect to this particular choice of basis. So this becomes somehow the signature of the vector. But this depends on which basis you're using here, right? So think of basis as like a currency, right? If I say US dollars, right, then you have $10, right? Then you can only, like, you have 10 US dollars. But if I change basis, meaning change the currency to euros, then you can change $10 to, I don't know, like maybe 7, 8 euros, right? Then essentially this is exactly what we meant by change of basis. We want to see that, okay, you have a coordinate of a vector, which is the coefficient for the linear combination, right? I have a certain coordinate with respect to one particular choices of basis. Once I change the basis, my coordinate will change, right? Because the foundation changed. But what's the correlation between these 2 different coordinates? And that's exactly the topic we want to discuss, right? Think of change of basis as if you're changing the currency, right? You want to switch from dollars to euros or euros to like back to dollars or different kind of currency, right? Then you want to see that what's the correlation here. Okay, so I want to start the 3.5 using this as a motivation. Then, like, first of all, make sure you catch up until 3.4. And if you could, it's highly recommended that you start preview the 3.5 so you can kind of catch up here. Okay, so if you have any question, feel free to stay. Otherwise, you're free to go.
Professor,
Mm-hmm.
I have a question from section 3.3,
Yeah. Mm-hmm.
exercise 4B.
4B.
I know what I'm supposed to do, but
Mhm.
what throws me off is how the vectors are put in the problem. I don't know. It's like a 2 times 2
Matrix. Yeah. Okay.
Yeah.
So let me share. Let me do this here. So you want to 4B, right?
Yes.
Okay. So you want to check that whether they're linear independent, right? So think of that each matrix is like one vector, right, in the space. So you code it A1, A2, A3, right? So you do the same thing, right? You want to solve that C1 times A1 plus C2, A2 plus C3, A3 equals 0, right? But now since we are dealing with a general vector space, so the 0 is not the 0 vector, right? So let me ask you this question. What would be the 0 element in 2 by 2 matrix space?
0, 0, 0, 0.
Yeah,
like
exactly.
Okay.
Yeah. So you want to solve this, right? And you want to see that solve this, and your question is, what are possible solution, right?
Yeah.
C1, C2, and C3. If they all have to be 0, then this means it's independent, right? Because that's the unique trivial solution. If you could find some non-trivial C1, C2, and C3, then it's dependent. But then, okay, then this one is actually not too bad at all. So let's see. So because we already have explicit metrics, right? And metrics quite rigid. So C1 times A1, if you multiply it, it will be C1, 0, 0, C1, right? This just multiply a scalar number to A1, right?
Yeah.
And then you plus C2 times A2. So this is would be the matrix plus C3, A3. And you want it to be 0, 0, 0, 0. Okay, let's combine the left-hand side. So you obtain something like this. No, C1, C1 here, sorry. So let me ask you another question. When we say two metrics to be equal, what do we really mean?
That each component has to be equal.
Yeah,
Right?
yeah.
So this is only true for C1 equals C2 equals C3 equals
exactly, yeah. So then in that case, we only have unique solution because we know we cannot have something else. It has unique trivial solution.
Okay.
Then that means it's independent. Yeah.
Oh, okay. Yeah.
Yeah. So actually, you can see the matrix is actually easier than vector, right? Because when you compare metrics, it's very rigid. It's very restrictive in some sense, right? So this pretty much you can directly see, unless from the if in some bad case, right? Unless when you equal things, you might actually, for example, depends on the situation. Like this one, because A1, A2, A3 are very easy. But you might, in some more complicated example, you might have something very, I don't know, complicated, right? Let's say you might have something like this, right? And equals 0, 0. Then you really need to say, okay, I want C1 plus C2 to be 0, C1 minus C3 to be 0, C1, and then you need to really solve it, right, in terms of the equation.
Right.
You might have that, right, in more complicated example. But in this case, because it happens that you only have one coefficient in each entry, so there's no other choices to be, yeah. So that's the case. Yeah, in this case, it's actually not too bad at all. Yeah.
Right. Okay. And the other question that I have is for 9A.
9A, same section.
Same section, yeah.
Okay, 9A, yeah.
So again, the same idea. I put the C1x1 plus C2x2 has to equal 0, and then if that's the case, then the cosine of pi x and the sine of pi x has to be 0, right?
Okay, so be careful here because now you're dealing with functions, right? How do you know, right? Then the functions are more tricky in the sense that then you also need to make sure, because the things that like the function would depends on the value of x you choose, right? So either if you want to do this way, it will be harder in the sense that then you need to pick certain value of x, right? Because these are all concrete number, right? The one you just did. But sine of pi x and cosine of pi x, this will be different if you plug in different value of x. There's several ways of doing this. First thing I would ask you to do is try the Wronskian, right? Remember that actually we do have the Wronskian in this section. That's also one of the reasons that I want to assign this problem. Yeah. So when you see instead of just like some usual matrix or like usual traditional vector, if it's functions, then first try the Wronskian, because Wronskian, if the Wronskian is not 0 at certain point, then right away you know it's independent. So essentially, I could refer you to actually the page before, right, when we talk about the Wronskian. So you can check the Wronskian of these two functions. It shouldn't take too long to check, and this is the way that you can avoid solving the equation you just said, right? So Wronskian is okay. You check the determinant of the first row will be, it doesn't matter which one I put it first. Okay, let's swap the order since that's the order the textbook used, even though it really doesn't matter. So let's say if the Wronskian of this, then first row is the function, right? And second row is the derivative, right? Then you see that whether the determinant is actually non-zero. So if you want linear independent, right? If this is non-zero at one value of x, then it's independent. This is essentially the, let me see, this is theorem 3.3.3. And exactly the whole point why we introduced the Wronskian. Try this first, unless it's completely 0. then you go back to use the equation you just said. Yeah.
Okay.
Yeah. So I would say, if I remember correctly, I think this should give you non-zero. If it's 0, then you can take a look at the example, what's this example? Example 9 in this textbook. Again, like the page before this exercise page, right? You can kind of take a look that if Wronskian is unfortunately 0, then you really need to go back to the definition. But to use definition on function like this, it's more work, I would say, in some sense. I'm not saying your method was wrong. Your method is still correct, but it would take much more time. Yeah.
Yeah. Okay.
Okay. Yeah. Try this. Yeah. You're welcome. Any other questions?
Yeah, actually, I wanted to ask about number 20.
20. Which section?
Is it 3.3? I think. Yeah.
Okay. Yeah. So that V1 to Vn be linear independent vectors in space show that cannot span V. Okay. So so what's your thought on this one?
Well, I just like wrote out like an example vector first, and like.
So I mean, this is very abstract, right? This is actually the hardest homework problem in this section, because this is very theoretical. But I want to challenge people to do this. Okay. So first of all, we don't even know what the vector space V is, right? It can be any vector space we know of, right? So like to deal with this problem, you should not just pretend V to be a specific vector space, right? Because you're actually trying to prove something very general, like a general, like a statement, right? Like for example, if I say that, oh, someone living in the Earth, you cannot say that, oh, assuming that person living in the US. How do you know, right? So that in this case, you're trying to say a general statement. So usually the trick for proving things like this, we want to do something called proof by contradiction. Okay, so let me rewrite the thing. So we want to say assume V1, V2, Vn are linear independent, right? This is what we know to start with, right? And it's linear independent in the vector space V, right? We want to show or prove, we want to say that is this imply that if we only take some of it, say from V2 to Vn, it can't span the whole V, right? So this basically tells you that, okay, I have assumption to start with. I want to prove my conclusion, right? In the logic, this is what we call, if you have a statement P and it implies Q, right? I want to say if I have P, then Q is right. But actually one way to show this is an equivalent statement. Equivalent statement is to say that one way to show this is if Q is not correct, I want to show that if not Q or negative of Q implies not P. Let me use this logic. If I said that, okay, if I live in Wichita, I live in Kansas, right? We know this is true. But another way to prove it is that if I don't live in Kansas, I cannot live in Wichita, right? So this is essentially the logic here. So I want to say that, or in other words, maybe let's put this way. I want to show that this is the case, right? V2 to Vn cannot span V. So what I could do is, what if this is wrong, right? What if it can span V, right? What if V2 to Vn really span V? If this is the case, I should be able to reach some contradiction, right? So assume the contrary, right? Assume V2 to Vn can span V, right? And our goal is to hope to reach a contradiction, right? Then that means something is wrong, right? Does that make sense?
Yeah.
Okay, so let's see what happened if we assume, if we say, okay, what happened if V2, Vn span V, right? So what happened if this is really the case? What happened if the span, the span of V2 to Vn is really V, right? Okay, so do you agree that V1 is a vector in V,
Yeah.
right? But now I say, oh, V2 to Vn span the whole V, then that means since V1 is in V, right? So V1 should be a linear combination of V2 to Vn, right? Because that's the definition of having a spanning set, right? Because now you say that, oh, let's assume it could span the whole V. But then I know V1 is one of the vector in V. So then technically then V1 should be able to written as a linear combination of V2 to Vn, right? Whatever the linear combination is. So I say, okay, then I actually could do this, right? That's called as coefficient like this. Okay, did you see something bad here? If V1 can be written as a linear combination of V2 to Vn, does it contradict to something we know to start with?
Well, you're saying that V1 is a part of the set of vectors that make up V, but now you're saying that V1 is also equal to everything inside of V, besides itself.
No, so what I'm saying is that, okay, you start with, let's back up a little bit. This is actually much harder, so I want to slow down here. So I start by assuming, so our assumption is, I already know these n vectors are linear independent, right? No matter what, we always have this, okay? So I know these n vectors are independent with each other. This is what we always have. Now I want to say that if this is the case, then if you only pick some of them, say V2 to Vn, if you omit one of them, right? Then this n-1 vectors cannot span V. So my idea is, okay, I want to see that if I assume the contrary, if I say V2 V to Vn really span the whole vector space, can I find something weird or find something that contradicts to something we already know? So I say, okay, forget about what I said about logic. Maybe this is too much. Then I say, okay, assume the contrary. If V2 to Vn really can span V, what would happen, right? What went wrong? So I say, okay, then span, let's say span of V2 to Vn is V. What the spanning set means, it means any vector in the vector space V should be able to be written as linear combination of your spanning vectors, right? Because I claimed that, okay, V2 to Vn is the span of V2 to Vn is the whole space, right? So any vector in my vector space should be able to written as some linear combination of V2 to Vn. I don't know the exact what's the coefficient, but it can be a linear combination. So my question is, okay, then the trick is, okay, I know V1, the one that we omit, is one of the vector in my vector space. Then by the fact that we assume V2 to Vn are the form the spanning set, then V1 is an element in V, right? Whatever that is, should be able to be written as a linear combination of V2 to Vn, right? So I write V1 as some linear combination of V2 to Vn. But if I can do that, then you can see this tells me that then V1 depends on V2 to Vn, right? Yeah. This is exactly what we don't want to see, because then right away, if you have this, then you're saying V1 to Vn are not linearly independent, right? This is something that we actually discussed in the beginning of 3.3, right? If you see this, right, while one of the vector can be written as linear combination of the others, then that means they're not independent. And this contradicts to what we start with. Right? Because we start with by the assumption that they are linear independent. So you can see that that's where the contradiction is, right? You want to prove something, then you say, oh, what if that thing is wrong? Can we reach a contradiction? That's the trick here. So we want to prove that this V2 to Vn cannot span V. So what we did is, oh, what happened if it could? And we realized if it could, then it will make V1 to Vn not independent. Then it violates what we start with, what we had. So then it tells me then this just means that then what we assume here is wrong, meaning then V2 to Vn really cannot span V, right? Because if it could, then it brings something contradiction. It brings something to lead to the contradiction. And this is actually hard because this need to test you. How do you know to create some kind of contradiction like this? Plus, you need to know that once you have the spanning set, right, then you need to reach the contradiction where V1 could be a linear combination of the other. And then that tells you that, oh, then it violates what we know. Yeah.
Okay.
Yeah, this is actually a very challenging question that I was actually thinking whether I should include this, but I want to actually challenge people, and like this is the way that I push like the knowledge, see whether people can actually think about that. Oh, what if like is it certain things imply the other thing? And then this also exactly tells you that in certain situation why we know that if we know the dimension, right, then you cannot have less vectors. Yeah.
Yeah, I think it's what happened here is like I tried to kind of work backwards since I saw a bit of 3.4, and I basically tried to reach
that's
around.
exactly why I'm saying that. Yeah, that's exactly why I was worried, right?
Because that was like my line of logic initially. Then I realized like, wait a minute, I don't know if I have enough information to just like straight up prove that.
Yeah, exactly. So yeah, so you need to be careful. That's why I was worried that people use a future knowledge or maybe misunderstand or misuse, then there will be a problem, right? So that's why I, like today, a lot, like some of the students ask me. So I want to say that like if you are in 3.3, then avoid using the future knowledge, because how do you know maybe the thing you are proving now is the key proving the fancy knowledge you are using, right? So there will be a like a loop of logic, right? Like for example, how do we know like the multiplication? We like table or something like that. We start from addition, right? So if you cannot prove certain things in addition, you should sometimes you cannot get the conclusion about multiplication, right? So there's a then if you use the future knowledge or future things on the current thing, then there might be a loop, right? Like, so you want to be a little bit careful here. That's why the safest thing to do is if you're in certain section, just use the section. There's a reason that they put that question in that certain section. Yeah. So yeah. I'm glad you asked. This problem is not easy. I was expecting people to ask me though. Yeah.
Yeah, I did it on accident because I just thought of it like intuitively, like, oh, you need like 3 vectors to make like 3 space. You need like 5 vectors to make like V.
But this one that you don't know, right? Because they only tells you this n vectors are independent, right? They didn't really tells you this n vector form the spanning set of V. So things you ask, right? This number 20 here, they only tells you V1 to Vn are linear independent in V, right? But they didn't tell you at all whether the span of this vector is V or not, right? You might, for example, in R4, right? But I could say I have 3 independent vectors, right? That's possible, right? So then you don't know what's the dimension of V at all in this particular problem. That's why you cannot even use some of the theorem we mentioned today or in 3.4, right? Because you actually, for this problem, you don't have enough information to determine what's the dimension of V. The only thing you can say is it will be at least n, but it might be more than n, right? Because what you don't know is whether these n vectors and linear independent really span the whole vector space V or not. We don't know. So they are not necessarily a basis yet. So you want to be a little bit careful. This is what, so you want to distinguish the concept of being linear independent, spanning set, and basis. They're kind of different. They're related, but not exactly the same.
All right.
Yeah.
Okay, well, thank you.
Yeah, you're welcome. So any other questions?
Not for now. Thank you.